Hello, thank you for watching this video. So in this video I'll be doing question 10 of November 2020 question paper, Physical Sciences paper 1. So I'll be doing question 10, which is the photoelectric effect. I will read the statement and show the question paper like I always do. Hopefully you will find this video helpful. An experiment is conducted to investigate the relationship between the frequency of light incident on a metal and the maximum kinetic energy of the electrons emitted from a metal. This experiment is conducted for 3 different metals. The graph below represents the results obtained. Let me try to read this again. An experiment is conducted to investigate the relationship between the frequency of light incident on a metal and the maximum kinetic energy of the emitted electron from a metal surface. The experiment is conducted for 3 metals. The graph below represents the results obtained. So, first question, 10.1. Name the phenomenon on which this experiment is based. So they want you to name the phenomenon on which this experiment is based. So 10.1, that phenomenon is the photoelectric effect. So that phenomenon is the photoelectric effect. So this phenomenon is observed when a light incident is shown into a metal, and electrons are observed to be ejected or emitted from a metal surface. So that's what photoelectric effect is. So let's go to 10.2. Name the physical quantity represented by X on the graph. Name the physical quantity represented by X on the graph. So they were asking what is this physical quantity that is represented by the graph, by X on the graph. So 10.2, that is the work function of your metals. Work function. 10.3. So question 10.3 reads as follows. Which one of the three metals needs the light with the largest wavelength for emission of electrons? Give the reason for your answer. Let's read the question again. Which one of the 3 metals needs the incident light with the highest wavelength for the emission of electrons? Give the reason for your answer. So they're asking you which one of these metals, which is your potassium, your zinc, and your platinum, will need the longest wavelength for electrons to be emitted, right? So we say that, okay, you know that your frequency is inversely proportional to the wavelength. Frequency is inversely proportional to the wavelength. So now, the light that requires, or the metal that requires the highest frequency for electrons to be emitted, have the smallest wavelength, because the higher the frequency, the shorter the wavelength. The higher the frequency, the shorter the wavelength of that light. So, in this case, the metal which requires a high frequency, a very high frequency light will have the shortest wavelength, and vice versa. If you're looking at these metals here, the metal which requires the lowest frequency is the one that is going to have the longest wavelength, because, as I said, the frequency and the wavelength are inversely related to one another, are inversely proportional to one another. So in this question, they are asking you which metal requires an incident light that have the longest wavelength. Because I said the frequency and the wavelength are inversely proportional to one another, the metal that requires the smallest frequency is the one that will require the incident light with the largest wavelength or the longest wavelength. That's what you deduce from the inverse proportionality relationship. So by looking at these metals, potassium, okay, have the lowest frequency, right? And platinum have the highest frequency. So the higher the frequency, the shorter the wavelength. The lower the frequency, the longer the wavelength. So this one, which is potassium, that have the lowest frequency on these metals, is the one that is going to have the longest wavelength, because the wavelength and the frequency are inversely proportional to one another. So they're asking you, which of these three metals will have the longest wavelength? The one that will have the longest wavelength is the one that have the highest frequency. And by looking at this, it should be potassium. So potassium K will have light with longest wavelength. This is it. So this potassium metal is the one that will have the light with the longest wavelength, because it has the lowest frequency. So the frequency and the wavelength are inversely proportional to one another. So let's continue. So define the term work function in words. So work function, it is the property of a metal. So work function differs according to metals. So you see here, look at this, look at that. All these metals have different work functions. This one, potassium, have the smallest work function, and that one, platinum, have the highest work function. So what is the work function? It's what we are asked to do. So the work function, like I said, it is the property of a metal. It is defined by a metal. So what is work function? So work function, it is the minimum energy required by a metal for electrons to be emitted from the metal surface. So it is the minimum energy that the light must have in order to emit electrons from a metal surface. So that energy, that minimum energy, is not the same for different metals. It varies. So the minimum energy that you need to emit electrons from a metal depends on the metal in question. So work function, it is the minimum energy required from the incident light for electrons to be emitted from a metal surface. And the work function is a property of a metal. It depends on a metal. It is defined by a metal. As I said, these metals have different work functions. All of them, they have different work functions. So work function, it is the minimum energy required by a metal from an incident light for electrons to be emitted from a metal surface. I'll write it down, 10.4. So here is it. So a work function, it is the minimum energy required by a metal from an incident light for electrons to be emitted from a metal surface. So the work function is defined by the metal. It differs from each metal. So that each metal requires certain energy for electrons to be ejected from that metal. So that's what work function is. It is a property. It is a property of a metal. Let's continue. 10.5. Calculate the work function of platinum. So they want us to calculate the work function of platinum. So with our platinum, go back. So here's platinum here. So its function, its frequency is 1. Okay, so I will not be able to see this exactly from this diagram. I'll look at it on. I'll look on it on our accurate on your drawings, which is on your drawing, on your question paper. So starts, there's a small dot here of some sort. There's another one here. There's another one there. So you can see this is 0, 0.25, 0.5, 0.75, 1.0. So there should be 1.25 somewhere in between here. So this is 1.75 essentially. Right? So they want us to calculate the work function of this guy. So we do have our threshold frequency there, which is the minimum frequency required for the minimum frequency required for electrons to be emitted from a metal surface. This is our threshold frequency. So if you have a threshold frequency, you can be able to calculate the work function. So say, okay, work function, which is this, is equal to H times threshold frequency. Your H is equal to Planck's constant, which is 6.63 times 10 to the minus 34 times your threshold frequency, which is 1.75 times 10 so 1.75 times 10 to the power 15 times 10 to the power 10 to the power 15 times 10 to the power 15. So this is 10, sorry, 10. So you can punch this in a calculator. 6.63 times 10 to the minus 34 times 1.75 times 10 to the power 15. This is your work function is equal to 1.16 times 10 to the minus 18 joules. Done this, 10.5.2. What does it say? 10.5.2, calculate the frequency of the incident light that will emit electrons from the surface of platinum with a maximum velocity of 5.6 times 10 to the 5 meters per second. Calculate the frequency of the incident light that will emit electrons from the surface of platinum with a maximum velocity of 5.6 times 10 to the power 5 meters per second. So they want us to calculate the frequency of an incident light that will emit electrons from the surface of platinum. And those electrons will be having this velocity that we're given here. So how do we do this? Say, okay, the energy of an incident light is equal to work function plus kinetic energy. So we do E of a light is equal to work function, which is 1,16 times 10 to the power minus 18 plus half m, which is the mass of an electron, which is 9,11 times 10 to the power minus 31 times velocity, which is 5.6 times 10 to the power 5 all squared, kinetic energy. So E of a light is equal to this. So we say 1,16 times 10 to the power minus 18 plus 0.5, 9,11 times 10 to the power minus 31 times 5.6 times 10 to the power 5 all squared, which is 1.30 times 10 to the minus 18 joules. So the light, the incident light, must have, or the incident light have this energy. So now, but they said they want what? The frequency. So the incident light have this energy, but they want the frequency. So to do this, we say, okay, the energy of a light is equal to HF. We do have this to be 1.30 times 10 to the power minus 18, which is equal to HF, which is 6,63 times 10 to the power minus 34 times F. So you divide this both sides. 6,63 times 10 to the minus 34. So you divide this both sides. So this side will be left with F. Which is equal to 1,997 times 10 to the power 15 hertz. This is the frequency. So this is the frequency of your incident light. And this brings to the end of our question. I'm so sorry for the noise, and it's very dark, load shedding. Welcome to Mzansi.